You know that since v of z and a of z are probability generating functions, so v of 1, a of 1 are equal to b1. So using that relation, you can find out what is the value of v naught. So v naught is nothing but 1 minus a dash of 1, and a dash of 1 is nothing but the expected arrivals. Just now we got expected arrival is equal to rho, therefore v naught is equal to 1 minus rho. So earlier we got Vz in terms of a of z with the v naught, and already we have the relation a of z is a Laplace transform of a probability density function of service time distribution, and just now we got v naught in terms of 1 minus v naught is equal to 1 minus rho. Therefore, the probability generating function of the steady state probabilities will be in terms of Laplace transform of a probability density function of a service time distribution with rho, and this equation is known as a Poloczyk's-Kenshin or PK formula. So this is the formula used to find out the steady state probabilities, because if you get the coefficient of z, that is the steady state probabilities. Note that the quantities of interest are the steady state probabilities at a different set of points, namely the arrival epochs. From the point of view of arriving customer, the number of customers that he finds in the system, not the number he leaves behind, is the quantity of interest. Since the arrival follows Poisson process, the equilibrium distribution of the number of customers found by the arrival and the equilibrium distribution of the number of customers left behind by a departure in this queuing model are the same. Note that the MG1Q, the limiting distribution of the number of customers in the system at the arrival epochs, at the departure epochs, and at the arbitrary time points are the same only since the arrival occurs as a Poisson process. So we found the limiting probabilities at the departure epochs, but since the arrival follows a Poisson process, the limiting distribution of number of customers in the system at the arrival epochs and the departure epochs and at the arbitrary time points all are same. This is a standard result which we shall be using without proof. Now we can find out the average measures. Average number of customers in the system in steady state is given by differentiate the probability generating function and substitute z is equal to 1 will be the average number of customers. If you do the simplification, you will get rho times rho plus lambda square expectation of the service time distribution whole square expectation of b square divided by 2 times 1 minus rho, and this equation is known as a PK mean formula. The previous one was the PK formula because that gives the steady state probabilities, whereas this gives the average measures, therefore this is called the PK mean formula. Here expectation of b square is the second order moment about the origin for service time. This result holds true for all scheduling discipline in which the server is busy if the queue is non-empty. The expected system size Ls can be computed without Vz also, because if you know rho as well as if you know the expectation of b square, you can find out the expected system size. Now we are deriving the Ls in a different way, not via the PK formula. So the derivation is as follows. So the Ls can be written in terms of expectation of xn plus 1, and you can find out expectation of u of xn using this. You will get it's equal to rho, and after you do the simplification, you can get the expectation of xn plus 1 square also in terms of expectation of xn square, as well as expectation of an square. So once you know the expectation of xn plus 1 square and the variance of arrival, where variance of arrival means the variance of number of arrivals during a service time, you can get the expected number of customers in the system in steady state. So this is called the pk mean formula without using the pk formula. Once we know the LS, that is average number of customers in the system, you can find out the LQ, that is the average number of customers in the queue, and TS is nothing but the total time spent in the system, and the TQ is nothing but the TS is nothing but the average time spent in the system, and the TQ is the average time spent in the queue. So using Little's formula, you can find the all other measures. As a special case, if the variance is 0, variance of service time is 0, that means it is a MD1 queue, then you can get the average number of customers in steady state will be rho plus rho square divided by 2 times 1 minus rho. Here the rho is nothing but lambda by mu, where 1 by mu is a constant service time. Alternatively, you can find out the steady state probabilities by solving a V is equal to Vp, and you can use the mean sojourn time, that is 1 divided by mu j for the state j. Then you can find out the steady state probabilities. Pj is nothing but average sojourn time multiplied by the steady state probabilities of embedded Markov chain, the way we have done it in the semi-Markov process. As a special case, you can verify when the service time follows exponential distribution with the mean 1 by mu, you can get the one-step transition probability matrix in this form for the embedded Markov chain. Then you can solve V is equal to Vp with the summation of Vi is equal to 1, you will get Vj's. Then if you substitute the Vj's as well as substitute the Vj's, then you can get the steady state probabilities for the M1 Q, that is same as 1 minus rho times rho power j. For any MG1 queue, you can find out the average time spent in the queue, that is a mean queuing delay. And once you know the mean queuing delay, if you add the average time spent in the, you can get the average time spent in the system by adding average service time, that is 1 by mu. So the TS will be TQ plus 1 by mu, that will be the average time spent in the system. By Little's formula, you can get LS. LS equal to lambda times TS. You know the TS, so from that you can get the lambda S, which is same as what you got it in the pk formula, pk mean formula. As a special case, when the service time is exponential distribution with the mean 1 by mu, you can get the average time spent in the average number of customers in the system will be rho divided by 1 minus rho. This is same as the average number of customers in the M1 queue. In this derivation, we assume first come first served scheduling to simplify the analysis. But the above formula are valid for any scheduling discipline in which the server is busy if the queue is non-empty. The no customer departs the queue before completing the service, and the order of service is not dependent on the knowledge about the service time. If these conditions are satisfied, then for any scheduling discipline, you can use the above formula of average number of customers in the system. So using Little's formula, you can find out the average time spent in the system. Lambda times t is equal to Ls. As a simple example, consider the people entering cricket stadium at New Delhi to watch the cricket match. There is only one ticket line to purchase tickets. Each ticket purchase takes an average of 20 seconds. The average arrival rate is 2 persons per minute. So the question is, find the average length of queue as well as the average waiting time in queue, assuming the queuing model is a MG1 queue. With the service follows a uniform distribution between 15 to 25 seconds. With this given information, you can get the departure rate, arrival rate. Because it is 20 seconds per person, therefore the rate will be 3 persons per minute. And the arrival rate is 2 persons per minute, therefore you can get lambda, that is 2 by 3. So it is a irreducible positive recurrent Markov chain, therefore the steady state probabilities exist. And given the steady service time distribution is uniform distribution between the interval 15 to 25, you can get the measures of steady state probabilities as well as all the average measures.